Good afternoon. Today I'm going to give a seminar. The title is Sea Ice Thermodynamics in Arctic Environment. We are going to focus on the observation and the modeling. And during this seminar, I'm trying to talk about the key parameter of sea ice thermodynamics. And then is followed by the observations. For in this part, I'm going to discuss some basic knowledge in terms of what I'm going to do, what I'm going to observe, and how to do the observation. And I'm going to talk about a little bit numerical modeling. So if you would like to do the model applicant, or if you would like to do the model development, and followed by analytical model. So in this part, I'm talking about a very simple methods, and it can also be used to solve some big question. And finally, I'm going to make a summary of all these discussions during this seminar. So let's start with our imagination. Suppose you are like a bird flying in the sky, and if you look down to the Arctic, and you probably see the ice flow in the ocean, it will drift there, and in between there will be some open water area. So this is really what it's supposed to be in Arctic. And in reality, we can even see that this image, it shows if you're flying with a helicopter, what you see is the Arctic sea ice during summer. So you see a lot of open water and open leads, and even some melt pond on top of the sea ice. So if we look even more closely to the scientific issue, let's say if you stand on top of ice and you do some measurements, and you can see the ice temperature and ice thickness and some time series. All these figures, it shows you some kind of annual ice thickness variation. The figure in the middle, it shows some numerical model results. And on the right side, these are some buoy measurements. So basically, you get some idea about what you are really looks like in the field. And of course, as I said earlier, so the ice is not stable, stationary there. It drifts from place to place. So this diagram is also shows you the ice drift in Arctic. So these things give you some impression of what the sea ice looks like in the reality, in the modeling, and in the numerical model result. And okay, so the first thing I would like to talk is about the key parameter of the sea ice thermodynamics. Let's first to identify what are the main key parameter of sea ice thermodynamics. And here, please use your imagination again. So suppose you are standing on top of this ice floe in the photo, like I showed in the photo. So basically, if you stand there, my question is, you want to go to the shore as fast as possible. So for you, what do you think? What is the most important parameter you would like to know? So you need to know ice thickness because you want to be safe. So let's say thickness, we can define it as one of the most important parameter for sea ice thermodynamics. And for this parameter, there's some consequent concept follow up to this parameter. So in this diagram I showed here, it's like how this ice thickness is evolved. So you see that ice is floating in the water. And at some point, you might have snow falling on top of the sea ice. And the whole system is moving upside down because of the gravity, because of the buoyancy. So the basic concept in here you might need to know is like ice thickness and snow depths and snow freeboard. The freeboard is refers to the distance between water level and either snow surface or ice surface. And of course, because the snow has certain weight, and if you have a thicker snow, then the snow might push it down and then to form the slush between snow and ice. And it can later be frozen to be a slush layer. And when it becomes solidation, and it can become snow ice. And in the summertime, when the surface is getting melt, and the melting of snow, it could percolate down to the snow ice interface and to form the superimposed ice there, and until the ice is totally melted away. So this shows you the time series of this ice thickness variation. So thickness is one of the most important parameters. Ice thermodynamics. Thermodynamics. Okay, so then you think that what is the quantity to describe that? Temperature, of course, everybody knows. So if we look at the ice temperature, so this figure, it shows the time series of ice temperature in the Arctic around a year cycle. So these are the very old observation made in 1975, when the Arctic sea ice is still very thick, like 3.5 meter. So basically from this figure, you can see that near the surface, the ice temperature can be very cold, minus 40 degrees. And down to the ice bottom, that is the temperature near the water, ocean. So the temperature is literally quite high. It's like a minus 1.8 freezing temperature. So for this quantity, if you look at how it changed in the idealized way, so we can basically to conclude, okay, in very cold condition, you get a very strong temperature vertical gradient between surface and bottom. And during the warm condition, like in summer, for instance, in the figure you can see in June and July, so upper surface is become warmer and the temperature gradient is become smaller. So literally the ice can be isothermal. So these are the variation of temperature. What else you can think about the key parameter of ice, sea ice? If you think about sea ice compared with freshwater ice, the major difference you might think already in your mind is the salinity. Yes, because sea ice is salty, fresh ice is fresh. And here I just shows some ice core sample to tell you visually what's the difference. So the ice core sample on the left, these are the sea ice core sample, where you can see that the ice texture is quite blurry and not very clear. Why? This is because there's a brine channel and the salt compartment inside ice. If you look at the ice core sample on the right, so these are the lake ice. It's quite crystal clear. So you see that that's mainly the air bubble or ice crystal there. For the ice salinity, so that is also linked with brine pocket, air pocket, and some substance within the sea ice. So these quantities, they are also linked with sea ice property, sea ice thermal property, and also possibly connect with sea ice biology, things like that. So these three parameters, in my opinion, we can define it as a very basic key parameter for the snow and ice thermodynamics. Thickness, variation in vertical direction, temperature in terms of temporal variation, and salinity in terms of do you have a salted ice or fresh ice. The second thing I would like to talk here is about these observations. For the observations, where we can think, okay, we're talking about the cryosphere. So in the snow and ice condition, it means cold, it means hard work. And also because of its harsh condition, it's also a team effort. we need people to work together. We need to coordinate to each other to accomplish the task. And also in the nature, there are different kind of dangers, different kind of things you might not want to meet. For instance, these two figures, it shows some wild animal there, polar bear, very cute, but I believe you don't want to stand nearby the instrument. The figure on below, it shows, okay, there are some holes on the ice. So this is also the last place you want to be on ice. So for the observations, I would like to first talk about some basic knowledge. So in order to carry out field measurements, there are some rule of thumb everybody should know. I can recall when I was a student, I learned from the professor, they told me the first things to do for the field observation is to keep yourself warm. That is very important. So keep your warm, that's the highest priority to do. In addition to this, you need also to be safe. And in here, this slide on the top right, I showed you ice peaks. This is something you would like to have when you're doing some ice work in the field. I'm happy to have one example of these tools in my hand is in here. So basically, this is something you have to do like that. When you go on ice, you always hold it on your neck and leave it there. And just in case, because sometimes if dangers happen, you might be falling into the ice below the ice floor, and then you use that trying to escape from the dangers. So this is very important. And we were recommended, like everybody, if you do the ice work, you need to have these ice picks. These are very important tools. Some other things you might need to know is like the field work. It means like many cases it's like one-time deal. You go on the ice and you do your measurement. You're not going back. So in this condition, in this scenario, you might need to be well prepared. So in addition to keep yourself warm, you need to have good gears. It's like you prepare some notebook, some waterproof pen, and on the camera, for instance, and you can record as much detail as possible in the field. So these are very important. And also, in addition, before you're doing field work, you might need to make rehearsal, try to understand, think about which step you are doing first and second and so on. So you make a clear plan. So then you get your better field work. And of course, when you're doing some measurements, another thing to be noticed is that you need to be careful. I mean, to handle your instrument and sample with great care, because sometimes if you break sample, if you break your tools, you have no chance to going back. So these are something you might need to understand. The basic knowledge of this field measurements, very important. And another thing I think is very important for the field measurement is like to keep it simple. Sometimes simple is the best. For instance, now if we talk about ice thickness measurement, so there are tens of different ways to do it. But most accurate thing to do is to just drill a hole and use your ice gauge to make the measurement. And once you have an ice core sample, and also you need to take a photo and make the contrast, put some black paper or black plastic behind it, so you can take a nice photo. So these are some very basic rules. And now, if we talk about observation, let's focus on one specified device. So we'll talk about the ice thickness measurement. For these things, we use the ice mass balance buoy. So there's, again, a different kind of complexity of techniques to do the ice thickness measurement. So in here, we say that, okay, one of the most classical instrument is ice mass balance buoy. and you used acoustic sounding to do the measurement, basically to detect the distance between your sensor and surface and the sensor at the ice bottom. And by measuring this distance, you can derive the ice thickness. So this is a very high tech and with quite big sophistication, and you can do it in a on a multi-year ice flow, or you can do it in the season ice flow. But now we are trying to talk about something else, something simple. Like I said, simple is best in most cases. So we are talking about this ice thermometer string, this kind of buoy. And this kind of buoy is nothing special. It's like it's mainly like a temperature chain. It deployed vertically through the snow, ice, and water, and you get the result. And this is called high resolution snow and ice mass balance array. It has been used in many different occasions in field works, as I summarized in here. These are very high profile field expedition, like Chinese National Arctic Research Expedition, or Mosaic. Everybody knows it just happened last year. So for doing this, we are trying to have two things to do. One is like you get your measurement, you are facing the data processing. So this is like you how to handle the data. And once you have your data results and you are going to do the data analysis, it's like to study the physics. So the first thing for this data processing, so the thermometer string, it's measured the temperature profile, as I said, vertically through air, snow, ice, and water. And the temperature, it can already tell you the different gradient inside different material. Like in air, the temperature is literally quite the same in the short distance. So basically, you see the profile is like a constant. But in snow and ice, because of thermal conductivity is different, so you get different result. And in the ocean, again, the temperature is quite isothermal. So based on this principle, you can, in a way, to detect the interface and then to finally derive the thickness. These are the principle of this device. In addition to the temperature, this device is also measure the heating temperature. The heating temperature means that you deploy your chains in the ice and you take the measurement, you apply a same exactly amount of energy to each sensor and let the sensor warm up and you record the temperature increase. Because sensor deployed in different material, so the increase of temperature is different in response to the heat capacity of the material you have deployed ice thermometer string. So in this case, the temperature increase will show differently. And by looking at those things, you can interfere or get the ice thickness. And in terms of analysis from the environment temperature, so we have trying to derive the algorithm to study to identify the thickness from the temperature profile. So there are some publications you can check in more in detail, but in principle, it's based on the continuation of temperature and of heat conduction. So then you can, in a way, to derive using some certain algorithm, certain criteria to get a result. And like I also said, in addition to the environmental temperature, the chain has also measured the heating temperature. The heating temperature is also possible to derive the interface. There's also some papers, and you can check. I have listed in here. So some of the paper is meant for the lake ice condition, and some of these are meant for the Arctic condition. So, and also some data paper also it shows there. If you are interested, you can look at all the temperature data and make your study based on this result. So this figure shows you the temperature change which can observe by the heating temperature and also measured by the environment temperature. So the interface it's derived, it shows the good result. And in addition, from this heating temperature, we see that it can give a quite accurate or kind of very striking time development of ice bottom, like the figure shows here on the left. So another work we are trying to do now is to use different mathematical methods to identify this interface. This is like, because you see the interface in here, but you want to get from the data, that is not so simple. And you need to use different kind of methods. So in this study, we are trying to apply a combination of, for instance, neural network is trying to get rid of this noisy data, and the wavelet analysis is trying to identify the variability of the interface, and then the Kalman filter to look how it goes in terms of time evolvement. So these are ongoing study, and you can see from the right, this figure, it shows quite nice comparison, the detection from this algorithm and the temperature from this heating profile. So, like I said, so these are the temperature measurement. We have talked about the Simba buoy, and this buoy has been deployed in Arctic, in different parts of the Arctic in different time period. And there's a lot of detail in here, but my main message from this slide is to tell there are quite many data available. It's free of charge. It's online. So if you dig at them, and you can use the data to do whatever you want to study, ice mass balance and snow and so on. So these are the information you can find from internet. Okay, so we have already talked about key parameter. We have already talked about field observations. And now let's talk about modeling. The modeling aspect, in here, I was trying to convince you like in which degree you would like to do the modeling. So basically, we can see any kind of model. It can contain two parts. One is like a physical part. So what are the physics you are really to describe by the model? Like for instance, the CI's thermodynamic model, you studied ice mass balance. You studied the thickness. You studied the thermal regime, temperature, and so on. And in all the models, you need to solve equations. So the mathematics is there. So in terms of if you want to be a model applicant, so you don't want to look at much detail of model inside, that's fine, that's okay. Then what you need to do is to understand the model input and the model output. If you understand these two parts, then you can basically run the model. You can do what? You can do your job. So this is, I call it model applicant. You don't look into detail of model physics or the mathematics. This part literally is like a black box to you. That's totally fine. But in another thing, another direction for you might be you want to further develop models. For these things, then you might need to understand a little better what the model is about. What are the physics? What are the mathematics? This method and all things like that. So, and this would require a little bit longer time and to look at more in detail. As one example, I can show you here. So the HiC model, this one-dimensional thermodynamic CS model, which I have been involved in the past 20 years to make development. So if you look at this model, basically you have you need to dealing with the three main parts. One is like surface heat balance, all kind of heat flux acting as the ice or snow surface, short wave radiation, long wave radiation, turbulent fluxes, and heat conduction, and so on. And followed by the heat conduction in the snow and ice. So this part is the heat conduction you want to deal with. And at ice bottom, so there's the heat and mass balance equation. So these are the basically three parts you need to dealing with. And when we talk about sea ice thermodynamics, we always think that the snow might be falling on top of sea ice. So all the things dealing with sea ice will automatically apply to snow. It may become even more complicated. And snow and ice is also interact each other, like I have shown you in the very beginning, the snow ice and superimposed ice formation. And if you would like to know more about this model, I have listed several references. I didn't show the title of the paper, but if you Google the author name and plus Heitze, I'm sure you will find all these information. So for this model, like I said, if you want to understand better and more things, and then you need to understand what the model is dealing with. And you need to build up the numerical scheme to solve the equation, because numerical model equation, it cannot be solved analytically. You have to solve it numerically. So what you need to do is like you have to build up your basic equation to tell you the upper boundary condition and the core equation and the lower boundary condition. And you need to discrete it to get a grid point, to get your results in different levels. And these are the ways to how to define the grid point in your model. There's different ways to do that. So these are something you might need to know better if you want to be a model developer. And something more about this Heitze model is like it's a one-dimensional thermodynamic model, but in addition, you can really calculate it in a two-dimensional way. So if you think like in one region, you have a bunch of different grid points. For each single point, you run this model and put the results together, you get the result of the domain. And here the open question is like in one single grid cell, you might have snow, you might have ice, or different kind of composition. So these are something it still need to be solved. If you would like to study that, that's your choice. You can continue to this direction. And of course, like I said, if you want to run the model as a model applicant, then you need to know what exactly the model input parameter would be. So in this case, is the weather forcing condition, and also the snow condition, initial condition. And if you want to run the model in the two-dimensional phase, you need to know the ice coverage, like ice concentration and things like that. So these are the model things, and that's quite complicated. Like you have numerical scheme and all the equations solved. But at some point for the model, if you pick up one single equation, you can still do some nice work. For instance, this equation is the ice bottom heat and mass balance equation. So from this equation, you can see that I have listed here. You have ice thickness data, you have temperature measurement, you have also salinity linked with the heat capacity and the heat of fusion and things like that. So over here, I want to say that these three key parameters, they are nicely combined to each other and placed in this equation. And if you have certain observations here, and you can find another terms, like for instance, this FW, that means the ocean heat flux. You can calculate it, identify it based on the field observations and based on this physical equation of the ice, how the mass balance change. Yes, so these are the some application of the model. And then now, if we look at the analytical solution, so at some point, this analytical model, it also works quite fine. it also tells you the basic idea of how the ice thickness and how the ice thermodynamic change. So how it works? Again, we come back to the equation I just mentioned you earlier. Heat and mass balance equation at ice bottom. If we apply some kind of simplification of this equation, for instance, we get rid of these terms, and then we further assume that the boundary condition on the top is the surface temperature and the bottom is the freezing temperature. And ice in react to this heat gradient. So then we can discretize this equation to get the analytical solution. So basically you just make some mathematical term to shift from one side to another and make integration and put the initial condition and identify the parameter, and then you can solve it. You can solve the H. That means the ice thickness. So this is like a very classical Stefan law. It already available in 1980s. So many like analytical model, you can assume snow on top. You can assume the heat flux from ocean below, and you can also derive a certain analytical solution based on some simplification of boundary condition. So this part is also very important if you would like to know like what is the basic rules, what is the baseline of ice thermodynamics. For instance, this Stefan law, it tells you the first order of magnitude of ice thickness. So the ice thickness, let's say if you know the temperature, if you use this assumption, you get the result. The result is not very far from the reality. The rest part, the numerical model, it solves something more in detail. And here, if you want to do the exercises, so here I just list very simple script. It shows this example of this Stefan law, how it works. So you need to play with the boundary condition like air temperature, like ice bottom temperature. The air temperature, it can also be like you know the time series of each time step, or you know only 4 times a day the temperature. And then basically you can make the interpolation and you find the difference is not much. It gave quite reasonable results, same result. Or the boundary condition is also like if you have a ice bottom, it can be a time-dependent situation or it can be constant. But the result is about the same because it's in the ice bottom, the temperature cannot change too much. But the initial condition, it tells you something. So if you use a different initial condition, so the ice thickness growth is literally different by the end of the simulation. So these are all, again, back to the very beginning. If you remember, I talked to you about the model in the beginning. You needed to identify the input condition. You needed to identify the initial condition and to know the result. So these are the something basically you can play with. Okay, so let's try to summarize what I have talked until now. So basically, we have identified the key parameter of CIS thermodynamics. Snow is the same thing. You have to think about that's part of the CIS thermodynamics. So the parameter, they are thickness, temperature, and salinity. And for the field observation, this is a quite large disciplinary. You can do a lot of in-situ observations, and you need to understand the safety. You need to be careful. You need to know the basic rules, and you need to know how to handle the equipment. Use as simple as possible. Or after you get the data, you have 2 things to do. The first, you do the data processing, and second, you analyze the data for the physics. Another thing is the modeling. So you do the modeling study, and you can be a model applicant. You use the model, or you can be a model developer. You develop a model. So these are 2 different things. All these things, it's back to linked with this slide. So Again, we talk about Arctic Ocean. We talk about sea ice thermodynamics. So snow thickness, ice thickness, these are the literally things you would like to know. And you can do it by observations, Zimbabwe, for instance. And you can do it by modeling, high-sim model. You can run the model, you can further develop the model. And in these things, some connection is linked with these are the ocean and atmosphere. And also in terms of the Simba, there are some techniques how to improve the device, how to make your instrumentation robust. And also there's also some process study, like you want to develop a model, how to better understand the atmosphere and ocean interact with Arctic Ocean and the result of the snow and ice thickness. So all these things I have marked in here is like you can dealing with technology is linked with observation. You can dealing with the physical process study is linked with modeling, model validation, model applicant, identification program, algorithm. So that linked with technology, the buoy. Spatial variability. So that means you need to deploy the equipment over the Arctic. So it's back to the original, this seminar, it meant to this integrated Arctic observation system. So we need to do a lot of measurement for the Arctic to understand it better. And so these things is continue even after the project is going to be end. For instance, like this buoy, we have deployed that in the past, let's say, in the past 10 years also. It's in particular in the past 3 to 5 years, there are many high-profile expedition program I have shown earlier already. So those buoys, some of these are already finished. I mean, like the lifetime is ended. The buoys stopped working, but some of these are still working. You can see in here, like some Zimbabwe, I have plotted in this figure. The data is ended until February 4th, 2 days ago. The buoy is still running, but I just plot the figure until this time. And and also this kind of platform is also very interesting. And I also would like to draw your attention. It's like Arctic expedition is very expensive. You need to go there, so that already costs too much. But you can use different kind of platform. For instance, on the right side, this is one of the French cruise ship, the test cruise ship. It's luxury cruise ship. And this kind of opportunity, scientific work, it also can be carried out on this kind of platform. Or like some coastal program on the top, on the bottom right, these are the field observation made by Danish Navy in collaboration with Aarhus University in Denmark. So they have deployed equipment in the Yangsund, east of Greenland coast area to do the measurement. And of course, in China, this Arctic January Expedition Program, annual program, it provides many opportunity to deploy a lot of instrumentations. So all these things, it can build up a very nice integrated Arctic observation system, which can be used to better understand Arctic, snow, and sea ice. So finally, if I want to summarize what we have learned here in this whole seminar, so we have identified the key parameter of snow and sea ice: thickness, temperature, and salinity. There may be some other parameter you think is more important. That's totally fine, but these are, in my opinion, very basic things. But the field observations, you know what's the drill, what's the most important. Keep yourself warm, keep yourself safe. Do with this life-saving tools. I'm saying this because I can tell you to the camera, I have once to see a people close to me, less than 2 meters in front of me, it's accident dropped to the below the ice. It's very dangerous. Without this, can be totally different. So I just try to draw your attention. This is very important. The safety issue is very important. Modeling issue dealing with heat and mass balance. And we can do the modeling, we can do the observation using buoy, we can do the modeling using thermodynamic standardized model. And sometimes the Stephen law analytical solution is also important. It also can be powerful to solve the problem. And here, by the request, I need to tell you some paper to read, some article, some books to read. So here are some suggestions. I think these are very good paper, very good articles or books. If you want to learn more about snow and sea ice thermodynamics, I would recommend you to check all these books and papers. Remember this? I showed you many times. Your lifesaver if you work on the ice. Even if you not like work, if you just recreation on ice, this is also very important, because I think you don't want, this is not a real condition. These are some training purpose, but you don't want to end up your last moment in the world like this. So be careful, be safe, keep warm on ice. I stop here. These are the seminar and do here. Thank you.